So this is an example of a problem called rationalizing the denominator of an expression that has radicals in it. And I have to just give a word of apology to, well, how do I want to say this? It is very difficult to motivate why you would want to do this. Why would we want to rationalize the denominator in an expression? It's a technique that you'll probably only use once or twice more in the future, maybe once in pre-calculus, probably a handful of times in your calculus class, but only if you take a calculus class that sets very sort of high expectations for the algebra that you would need to do. So this is a very advanced technique, and it's very difficult to explain why it's important. The short thumbnail answer for why this technique is important is that it's not really clear, it cannot be clear really to a mathematician, what it means to divide by an irrational number, a number like the square root of 3 minus 1. How do we divide by the square root of 3 minus 1? We know how to divide by rational numbers. If I want to divide by 3, I just want to find a number which added to itself with 3 terms gives me that original answer back. If I divide by 2/3, that's the same as multiplying by 3/2, and I know how to multiply by 3, and I know how to divide by 2. So any division problem that can be reduced to a question about dividing into whole numbers makes perfect sense. But if I don't have a whole number in that denominator, then it's not clear at all how we're supposed to divide by it in a way that makes any sense. So rationalizing a denominator is a way of avoiding that question, of rewriting this big fraction in a way that makes its denominator a rational number instead of the irrational number square root of 3 minus 1. So how does it work? What we want to do is to simplify this rational expression, simplify this fraction. To rationalize it means to do something to it, to make it so that its denominator is no longer an irrational number. Specifically, what we'd like to do is to make its denominator into a whole number if we can. That would be great. And the key to doing that, because our denominator has 2 different terms in it, the square root of 3 minus 1, what we're going to do is leverage the difference of squares technique, the difference of squares multiplication technique, to eliminate that square root term. And this works because if I have the square root of something plus something else, and then I have the square root of something minus something else, I multiply those 2 things together. The difference of squares technique is going to eliminate the cross term, the square root of a times b minus b times the square root of a, and leave me with just the square of the first term minus the square of the second term. And when I square that first term, the square of the square root of a gives me just plain a. So the difference of squares is the key to this technique. And the difference of squares applies whenever I have something plus something times something minus something, where we have the same somethings in both of those factors. The relationship between these 2 things are called conjugates. So the square root of a plus b and the square root of a minus b are called conjugate expressions. So our technique, if I want to rationalize the denominator, if I want to rewrite this fraction so its denominator becomes a whole number, is I want to first take that denominator and form its conjugate. And just like in the difference of squares, the relationship between its 2 factors, the conjugate of that expression is just going to be the expression we get by replacing addition by subtraction or vice versa. And then, if I want to turn the denominator into a whole number, I just need to multiply that denominator by its conjugate. But I can't multiply the denominator of a fraction by something without also multiplying its numerator by that same thing. So I'm going to multiply both the numerator and the denominator of this expression by the conjugate that we formed in step 1. Then I'm going to have a problem in this example of multiplying out binomial expressions, which equates to FOILing, right? Just distribute out the multiplication over the addition and subtraction, and then simplify everything in sight. So the heart of the strategy is zeroing in on that denominator, forming its conjugate, replacing subtraction with addition or vice versa, and then multiplying top and bottom by that conjugate. So if I have radical 3 minus 2 all over radical 3 minus 1, to rationalize this, I'm going to look at that denominator and say, what's the conjugate of that denominator, square root of 3 minus 1? Well, it's just the expression that we get when we replace that subtraction with addition. So the conjugate is square root of 3 plus 1. So to rationalize the denominator, I'm just going to multiply the denominator by the square root of 3 plus 1, the quantity square root of 3 plus 1. Don't forget those parentheses. But if I multiply by it in the denominator, I also have to multiply by it in the numerator, and that's where the fun part comes in. Now we just need to simplify. By FOILing, by distributing the multiplication across the addition and subtraction in the denominator, square root of 3 minus 1 times square root of 3 plus 1 becomes square root of 3 times square root of 3, that's 3, negative 1 times 1, minus 1, and then we'll also get the cross terms, minus 1 times the square root of 3, and plus 1 times the square root of 3, But when we add all those terms together, those cross terms are going to cancel, and that was the beauty of this technique. That's why we use the conjugate, is specifically because that cancellation is guaranteed to happen. And so what I'm going to end up with in that denominator is just 3 minus 1, which is awesome. That's going to be a whole number. Upstairs, same thing. 5 square root of 3 minus 2 times square root of 3 plus 1. If I multiply those out, 5 square root of 3 times the square root of 3, well, square root of 3 times square root of 3, by definition, is 3 itself. So that gives me 5 times 3, better known as 15. Negative 2 times 1 is going to give me negative 2. And then here come my cross terms. Negative 2 times the square root of 3, and 5 square root of 3 times 1. So I'll have 5 square root of 3 there. And the difference now upstairs is that we can't expect that those cross terms are going to cancel, and indeed they don't. So when we combine those together, 5 square root of 3 minus 2 square root of 3 gives us 3 square root of 3. So in the end, upstairs we'll get 15 minus 2 plus 3 square root of 3. And we've done all the hard bits. Now it's just a matter of simplifying. In my denominator, 3 minus 1 gives me 2, and we have accomplished what we set out to do. The denominator is a whole number. That's what rationalization is all about. But the numerator cannot be made into a whole number. All we can do is combine the like terms, and the like terms upstairs are just the whole numbers 15 and 2, whose difference is 13. And then I have plus 3 square root of 3. So to rationalize the denominator of an expression, zero in that denominator and say, what is its conjugate? And its conjugate means nothing more than replacing whatever addition we're doing of radicals with subtraction, or vice versa. When you then multiply by that conjugate both top and bottom, the denominator by its very construction is going to turn into a whole number. And the numerator is probably going to be some other nasty expression, which is fine. As long as the denominator turns into a whole number in this technique, then you have achieved your goal.